Hello everyone. Today we'll be joined by two speakers, Nadescha and David Barnes. Nadescha is a marine ecologist for the marine monitoring team here at JNCC, and prior to that has worked for British Antarctic Survey as a benthic ecologist in Antarctica, looking at how climate change impacts benthic ecosystems and dynamics. David is a benthic marine ecologist at British Antarctic Survey and is a visiting lecturer of Cambridge University. For the last 3 decades, he's been undertaking polar and remote island research, looking into seabed biodiversity and ecosystem services, as well as their responses to disturbance such as climate change. So without any further delay, I'll hand over to our first speaker of the session, which is Nadescha.
Thank you, Holly. As Holly said, I'm going to talk to you about how resilient shallow and active benthic communities are to climate change. And to do that, I have to take you onto a journey to the bottom of the world. It's not letting me, there we go. More particularly, or more specifically, the Western Arctic Peninsula, which you can see outlined here, and where we did most of our study. And so conditions around the Western Arctic Peninsula for little critters living on the seafloor are quite limiting and quite specific. They have a sea temperature which is ranging from 2 degrees to about -2 degrees. They have sea ice for the majority of the year, and that means a lot of darkness, so very limited light to photosynthesize. And then once a year, during a very limited amount of time, they get this influx of phytoplankton where they just can munch as much as they possibly want to. So it's already quite a tough life if you are some little thing living on a seafloor down there. And it's not being made easier by icebergs. So icebergs are pretty incredible things. They are massive or teeny tiny. They can have the size of a country. They come in all shapes and forms. They can be incredible sculptures, but when they are created, it's kind of when they break off the edge of a glacier is how they are created, or when an ice shelf collapses. So I don't know if you've heard about the big iceberg hitting South Georgia that had made the news in the spring. And so when they break off, they then move around the sea driven by wind and by currents, unless they are being immobilized in sea ice. And so for the majority of the year around the Western Arctic Peninsula, they should be immobilized in sea ice. And that means they're frozen in, they can't move, they're stationary wherever they are. So the dark side of the iceberg is what's underneath the iceberg. So literally what we see with an iceberg is the tip of the iceberg. It's about 10%, and the rest of the mass is underneath. And to kind of show this a little bit is I've put in this photo of the Rotherham dive team setting up their ice dive. You can see here is their dive hole through which they go through, and this is the general setup. And I want you to focus on this teeny tiny iceberg here. So as you can see, compared to all the other ones, it's actually not that big. And then looking underneath, however, this is in comparison with a diver, and this is a teeny tiny bit of an iceberg. So normally, yeah, I do apologize, I don't have very good pictures because it is quite dark underneath the iceberg, but underneath the sea ice is what I mean. But yeah, so you can see this is a small edge of the iceberg, so the rest of it is fairly big. And that means that that means that often icebergs, if you think about a 10-meter icebergs, which seems quite large, but it's actually not that big, you can, it's probably about an intermediate size iceberg, which then means that they have quite a far reach. If you have a 10-meter iceberg, you have 90 meters underneath, which means, yeah, they can reach quite a lot of the seabed with that depth. And they often get grounded on the seabed if they're being driven into the coastal areas. They often get grounded, and then driven by the wind or by currents, they kind of plow along the seabed, which means that everything in their wake is killed or destroyed. And you can see this here. This is bathymetry from the Arctic, but it's the same in the Antarctic. You can see these lines where the icebergs have just plowed through, and nothing in that wake. It's basically like a big trawler, so nothing in that wake will survive. So it's a very bad day for a normal kind of little animal living there. However, at a normal rate, this is completely fine and it's completely normal, and it helps to maintain the biodiversity there. So you can, for example, what we have here is an area that's been hit by an iceberg the previous year, and you can see there's different species in the assemblages. So you have here, you have a little starfish and you have some brittle stars. And then this area has not been hit for about 11 years. And you can see it's different animals living there. You have some sea cucumbers, you have different starfish. And then further on, if you go in an area that hasn't been hit for a very long time, you can see you've got these wonderful sponges and bryozoans growing up. And you see these are generally different assemblages. As many of you will know, having a little bit of disturbance maintains a lot of biodiversity. And why do we care? Why is all of this so important? Well, first of all, the Antarctic benthic communities are incredibly unique. They are specific to the Antarctic, so you won't find them anywhere else. A lot of them we don't even know yet that they exist, because sampling in this harsh environment is so difficult. And then it's also incredibly biodiverse, and it's something that people often don't think about, but it is almost as diverse as tropical areas. And then obviously we do get a lot of ecosystem services from them as well, which is something like blue carbon, which Dave will be talking about in a little bit. So all in all, quite important. And what specifically stimulated the study is a period between 2007 and 2009 where we didn't have a lot of sea ice around the Western Arctic Peninsula, which meant that icebergs were free to move a lot more than they used to be, which meant there was a lot more grounding on the seafloor, a lot more hits on the seafloor. And the study has shown that with this decrease in sea ice that you can see here, we have an increase in ice scour frequency, and with that, a decrease in immobilized carbon. So what we did is we went down to Rotherham Research Station, which is located on Adelaide Island here along the Western Arctic Peninsula. And we set up these different sampling stations. We can see here in the bay. So this is Ryder Bay, where a lot of the marine science happens. And then we have this little green triangle here where we have an icebergs impact study, which I'm going to talk to you about now. So to measure how intense iceberg impacts are on the seafloor, we use this incredibly unique sampling device of a concrete block. And we set them up in 25 times 25 meter squares, 3 squares, three grids per each depth, and 3 different depths, so at 5 and at 10 and at 25 meters. And what we then do is we monitor them once a year. We dive on them and we note down which of these blocks has been hit by an iceberg, which looks a little bit like this. And then we can link areas of the sea floor to years of disturbance and how often they have been disturbed and how long or how much time they had to recover since. So for example, we'd know that this square hasn't been hit for 11 years, and we know that this square over there has been hit the previous year. And the other thing we measured is ice cover. So we counted how many days per year we had ice cover. We counted, or we looked at phytoplankton duration. So we counted the number of days where we had peak of phytoplankton in the water column. And this is the Rotherham team going out once a week or as often as possible, going on the sea ice and sampling abundance of phytoplankton. And then we also looked at species richness. So we counted how much macrofauna we have, which is all the big stuff you can see here. So all the starfish, the brittle stars again, the sea cucumbers, and the epifauna, which is kind of small stuff that lives on rocks, you can see here. And we also looked at competition. So normally competition for space is quite important for animals living on the seafloor. And if you had an iceberg that's just gone through, there wouldn't be that much competition for space because everything has kind of been scraped clear. So species that would come in would settle far away from each other. And then as the communities kind of evolve and become bigger, competition for space starts to become an issue. So it's kind of a little bit of an indicator of the maturity of the community. And we use bryozoans to do this. And you can see here, so these are these colonial little encrusting animals. And you can see here this white colony is starting to be overgrown by this orange colony that you can see here. So we're starting to see competition occurring. And then we also counted or measured mortality, and we again used bryozoan as a proxy species for that. They grow because of the way phytoplankton only occurs once a year in a specific time period. Bryozoans grow in almost something like tree ring-like structures. And experts, which apparently I'm not one, can then distinguish the years at the age of the colony. And luckily, I have been working with experts, so they were able to do this. And what we then got was this plot. You can see the number of the years down here at the bottom. And we've got fast ice, number of mean icebergs hits per 25 meters square, mortality, species, spatial competition, and species richness. And we also got phytoplankton over here, but that wasn't actually significant. So we've left it a little bit on the side. And this blue bar marks the period of high disturbance that was such an issue. So everything before that was before the period, and everything after that is kind of the recovery period we're seeing. And as we've seen before, with a decrease in sea ice, we found an increase in icebergs hits. And that was very significantly linked with an impact, with an increase in mortality rates, a decrease in spatial competition, and very much so with a decrease in species richness for especially epifaunal species, and a little bit for the macrofauna or the megafauna here. And then we've got the recovery rate, and we can see that fast ice has started to increase again. It's still not quite back up to the same number of levels we had before, but it is getting there. And with that, we also see a decrease in icebergs hits. However, not quite as low as it was prior to that period of high impact. And that is also reflected in the mortality. We can see it is kind of decreasing, but it's still quite high. But we see spatial competition is starting to decrease. So mortality, so colonies are starting to become, evolve more. Not evolve. Evolve is the wrong word. Become older. That's the word. And then we see species richness here is also especially for the epifauna, is increasing dramatically towards after 10 years. It is similar to what it was prior to that period of high impact. And we also see it with the megafauna. We also see that increase here, which is, so we think why this relationship isn't quite so significant for megafauna as it is or for epifauna. We think this is because a lot of the megafauna is much more mobile than the epifauna is, and much less reliant on dispersion through larval dispersion to recolonize areas. So mobile species can just move into areas that have recently been hit. And that's, I think, why we're seeing a less pronounced relationship here. And so this is basically a short summary of all I've just talked about. And I think all in all, this is actually quite a heartening story. It's quite a good story. We see that the area that the Antarctic sea floor, which has such stringent conditions to deal with, is actually quite resilient to something as dramatic as they've experienced during this period of high impact. And so it's much more resilient than we expected it to be. It's much more resilient than, for example, a forest, which would take about an average 40 years to recover. And so it's really positive. On the other hand, it's also important to consider that, you know, as climate change is keeping to increase and is keeping to have an impact on areas, that 10 years might not be enough in future. These species, these animals, they might not get 10 years to recover anymore. And then we will start to see real changes in the communities we see down there. So a good news story. We're a little bit of a caveat at the end, I guess. And with that, I would like to thank the wintering team, the wintering marine team, and the wintering team overall, who've contributed so much to this study. And the wintering, or the marine teams overall, they've collected data for over 20 years on this study. So they're really a vital part of the marine science that's happening at Rothera. And yes, please let me know if you have any questions.
Perfect. Yep, you are all set and good to go.
So you can see the slide and you can hear me, yeah?
Yep.
Okay, well, I can't quite promise the levels of chirpiness and enthusiasm of Nadescha, but following along the same lines, but looking at a slightly larger scale now. So global climate change driven by anthropogenic greenhouse gas emissions is one of, if not the most important of societal challenges during the Anthropocene. Today, recognised nature-based solutions are on land or in the coastal shallows, and I'm sure we've all heard quite a little bit about that, especially in the news recently. But oceans form 70% of the planet and are the largest active reservoir of carbon, and they've been little considered, prioritised or protected away from the immediate coast. And the vast polar depths that we cannot walk up to or see from space to measure hit very important nature-based solutions criteria of being long-term, intact, extensive, and having a very high biodiversity with genuine carbon sequestration. I stress the word genuine, and I'll come back to that later. So low latitude marine carbon sinks, the ones that we're most familiar with, that I'll come to in a moment, are typically shrinking in size, and we do hear this on the news, the shrinking of mangrove swamps and so on. But on polar continental shelves, blue carbon, that is carbon bound within living marine organisms, is booming. And that's what I want to talk to you about in this talk. Right. So, blue carbon is a highly efficient carbon pathway. And when I say carbon pathway, I mean carbon is captured by photosynthesis of autotrophs. So typically if we think of plants, but it's not necessarily plants, it can be various algae and protists as well, and bacteria. And then some of this is lost in the form of respiration, and much of the rest of it is lost in microbial breakdown. What we would refer to as the microbial loop. So a recycling of that carbon initially captured. And so that's the basis of the carbon cycle. But some of it is consumed by animals and goes into carbon storage, but it stays in the bodies of organisms. Now, for those that are more familiar with terrestrial environments, most of the carbon stored there is in the bodies of the autotrophs that capture the carbon, most typically forests. But in the sea, it's very different because most of the autotrophs that capture carbon don't live very long. And so there's very little storage within those that capture it. So animals die, and when they're breathing, they respire some of that carbon. They lose a lot of it in the microbial cycle, just like the plants and the algae. And so we can see greater contributions to the carbon cycle. But a small proportion is removed from the carbon cycle, and that means typically burial, and not just burial, but burial below the oxygen layer. So below the top oxygenated layer of sediments, and how deep that is depends on what sort of particle sizes you've got. The smaller the particle size, the closer that layer is to the surface. And only then do you get genuine sequestration. In other words, the carbon has left the carbon cycling that I've been talking about and is above and become sequestered. And that's when it fights back against climate. That's when it works back as a feedback against climate. So polar blue carbon really does differ from that everywhere else, most of what we're familiar with. There are no mangroves, seagrass, meadows and salt marshes, where we think of as our high blue carbon environments. And production is dominated by phytoplankton, although there are kelp forests in polar regions too, and they're increasing and they're expanding along the coasts as coasts lose ice. And of course, there's phytoplankton everywhere else in the world. It's just that the polar blue carbon web is dominated by phytoplankton with some small input from kelp. So it's a little bit different to what we're familiar with. And this is something along the lines of how we can expect that pathway of carbon. Most of what we hear about is on the right-hand side of the slide, so that the sort of the larger predators, and they are a very small part of this pathway. The biggest pathway to sequestration is direct from the primary producers, which in polar parts of the world is phytoplankton and kelp. But you can see a fair proportion does pass into animals in the water column, pelagios, and those on the seabed. And then proportions of those travel through food webs, and proportions are buried. And something like 1% again comes from the animal chain. So we're looking at the realm of about 2% of the primary production being sequestered into sediments below. So let's look at an example of all of that on the ground. Biodiversity and blue carbon are very habitat specific. And here I've taken an example from some work we did 7 or 8 years ago around South Georgia, where we took various apparatus that were shipboard, and we sampled around the continental shelf. And just to give you an idea, that's about 40,000 square kilometres, the continental shelf around South Georgia. It may be a small island, but it's a big shelf. So it's quite an undertaking. It requires lots of specialist skills and lots of different pieces of apparatus. And in plot A, we can see how many organisms vary from place to place by the size of those symbols, and how many species, how rich it is by the shade. So black is highly biodiverse, white is very depauperate. And then if we move across to plot B, we can see the types of organisms that dominate are in different shades. And so really the only point that I'm trying to make there is that it's incredibly varied. And then if we move down to plot C, bottom left, then the size of the circles gives how much carbon is being stored on the seabed, and the colour gives what type of environments it's being stored on. And the red is the habitat of moraines, and these are created by glaciations when ice rolls out from the ice cap on the land and bulldozes large amounts of rubble right to the edge of canyons and to the shelf break, and leaves it there. And so you've got this relict habitat from 25,000 years ago that's extremely important now. And lastly, in D, we have to take cores, and we use a multi-core, and there we can look at the potential for sequestration, so carbon profiles in the sediment, how much of that carbon stored by animals is ultimately going to be buried. Well, it's a very complex environment with lots and lots of stressors that are increasing in both magnitude and variety. And this is just to give you a little bit of flavour for that level of complexity. The blue arrows indicate where an effect increases, red for decrease and black for change. And these can include increases and decreases. So yeah, just to give you a flavour of things going on, and we're trying to measure some of these, but of course we have the context, all of the others going on. So one of the things that is really striking is that marine ice, as Nadescha has given us an example of, is a very, very important component of these factors. And it's the biggest changing one, and it's composed of seasonal sea ice, that's the sea surface freezing, ice shelves where ice caps meet the sea and float, and these can be hundreds of meters in thickness, and glaciers that we're perhaps a little bit more familiar with. So to take those in turn, sea ice increases each winter, so it's seasonal, and recedes each spring as it melts throughout the summer. And it shows decreases, which I'm sure most of you have heard about, which are chronic in the Arctic. The fawn line, the sort of light brown line, so you can see there's noise in the signal, but overall a decrease which has been going for many decades. In the Antarctic, by contrast, the signal is also very noisy, but has showed an increase over that same period up to 2014, where there was a catastrophic collapse, losing in just 3 or 4 years as much sea ice as the Arctic had lost in 40. Since then, it's began to slightly increase again. So sea ice is a very, very difficult thing to understand and work with, and even IPCC models fail to recreate those patterns, which makes it very, very tricky for us. So from sea ice to ice shelves. So ice shelves are the extent of glaciers and ice caps flowing out to sea and forming very considerable environments, thousands of kilometres, where underneath it's pitch black and there is little change and little going on, and has been like that for perhaps hundreds of thousands of years. And those are starting to break up. You can see in red on the left-hand plot as a direct impact of anthropogenic climate change. And there's been particularly big collapses along there, generating what are called megabergs, giant icebergs. And we know very, very little about this environment. So from there, going to glaciers, which are a little bit more familiar, and you can see Rothera Research Station, or the position of it that Nadescha talked about, and a nearby glacier and its retreat pattern shown in years. And about 90% of West Antarctic Peninsula glaciers are in retreat, and this proportion is increasing, and their rate of retreat is increasing. And recently, Nadescha, myself, and a team of NERC-funded scientists across 5 universities were investigating exactly what this means to the biology and ecosystem functioning. And here we can see a schematic of that, whereby increased atmospheric carbon dioxide, i.e. greenhouse gas, in one, leads to decreased sea ice through warming, and that decreased sea ice means more light penetration, so potentially new and longer lasting phytoplankton blooms, the primary production, which means more food for animals on the seabed, which potentially means more burial and therefore a negative feedback on climate change because there is less carbon in the atmosphere. So that's very important because that means that we have the potential for a very valuable increase in production as a direct response to climate change, and we can measure that. And we've done that around several seas around Antarctica, and you can see A, the Scotia Sea in red, B, the Weddell Sea in green, and so on and so on. And so there are different patterns going on in different seas, but overall we can see that with sea ice losses, we have got increases in carbon drawdown, carbon going from being captured and stored to buried. So this is a good news story. However, these are modest carbon sinks if we compare them with Amazonia, for example. The size of the carbon sink is small, but we have to consider it's not the carbon sink that matters, it's how much of it is being sequestered and how it is changing in response to climate. And so these may be modest carbon sinks, but they are the largest negative feedbacks on the planet against climate change. So in other words, they increase as climate change increases, so they directly fight it, whereas most things decrease as climate change increases. So there's a little bit of just thinking around the difference between carbon sinks and negative feedbacks there. So we can go through some numbers on that. We can look at different changes in marine ice, and by far the biggest effect on sequestering carbon, or at least storing carbon, is in sea ice losses. And this is no surprise because sea ice is a huge habitat. Millions of square kilometres. So it is biggest in area, it's biggest in its effects on increased carbon storage as a result of sea ice losses. Next in size is ice shelf retreats, and next in the importance of carbon storage is likewise in that. And then, and you can see just pictures of the seabed of that carbon buildup. By comparison, fjords are really quite small in area and in terms of their carbon storage. But I put an asterisk by that, and the reason for that is that there is reason to believe that it's particularly effective at sequestration. It could even be as high as 25%, which is staggering compared to elsewhere in the world. I mean, for example, a forest in the countryside here might have 0 point something very small in terms of its sequestration. So all its climate potential is purely in the size of the forest. So you have to increase the size of the forest to make any difference whatsoever to climate. So sequestration does matter. So moderate warming also can increase carbon gain. So when I say moderate, we're talking in the realm of about 1 degree C, which we are in the realm of already. And given there is a lag factor around carbon dioxide emissions, we're already starting to look at possibly a 1.5 to 2 degree warmer world. And that may not increase gains. There is reason to believe through experimentation on a limited array of fauna by Gail Ashton and team that growth can be increased, and you can see the panel on the left at ambient temperature and the panel on the right immersed in seawater, all conditions the same apart from 1 degree warmer, shows increased growth and increased carbon storage. But if we increase that to 2 degrees, all hell is let loose. And how about recovery from impacts? Well, you've just heard a very enthusiastic talk about that, about looking at our longest term record of disturbance and recovery that I know of from anywhere in Antarctica, and has nicely shown that really we're looking at about a decade from impact there. That's where the level of ice scouring, and well, will that be enough? So in conclusions to all this, where is the low-hanging fruit of key nature-based solutions to aid us in greenhouse gas reduction? Protection of mature, intact habitat seems to confer best yield across the world, and potentially cost the least compared with restoration rewilding. These are still very important, but foremost, we need to avoid further ecosystem losses. We need to consider sinks versus feedback loops and storage versus sequestration. It's very important for us to understand what we're doing if the point is not just biodiversity conservation, but climate mitigation. And various recent work has really emphasised that we are careful with exactly how we go about that process if we want to make big gains, which we really need to do. A recent paper by Salo et al. That some of you may have come across shows just how little we have considered the ocean, and it lags by a factor of 3 behind the land in terms of protection. And the worst place is in polar, and yet, as I've explained to you, that's where the big negative feedbacks are, and that's where the big emerging carbon sinks are. So we need to do things a lot more smart. And if we look at marine areas, well, there's 2 relatively small ones in the Southern Ocean. I've just highlighted those in the Atlantic, and that tiny little one at the bottom around the South Orkneys is the only one in the Atlantic sector of the Southern Ocean. So in other words, we're starting to really understand blue carbon in polar waters, although we haven't quantified it in many areas. But as we lose marine ice and this becomes more available, we really do have to improve our synthesis across biodiversity and mitigation protection. Thank you all very much for listening.
Thank you, Holly. Thank you very much, David. That was an excellent talk and very well presented. Really fascinating to kind of get an insight into carbon capture and sequestration in the very, very far south. So we've got a few questions coming in, and we'll first go on to Nadescha. So the first one is, what is the predicted impact of climate change on iceberg score hits on Antarctic benthos, and is this frequency predicted to increase?
So we don't really have a prediction how much iceberg impact scours we have. What we found is that about 50% of the seafloor had been hit in this period. So presumably if we have less sea ice and more iceberg hits, this will increase, and the time of recovery will just not be enough for these systems to actually recover to previous statuses. So, but we don't have a trajectory, so to say, for that.
Okay, thank you. Next question. What is the first species to colonize an area of the seabed after an iceberg score or impact?
So you usually get all the scavengers in that munch up all what's left over. So we've got these long nematine worms. They're quite disgusting and very alien to look at. So they come in fairly quickly. You get a lot of starfish that come in very quickly as well. So mostly mobile scavengers.
If icebergs score down to the bedrock and remove sediment, do you see a difference in the species recolonizing, i.e. ones prefer rock to sediment, and how do you account for this?
So you do to a degree, but it's mostly bedrock anyway. So what you have is like cobbly areas in the shallows, a lot of cobbly areas with a like thin layer of sediment on top, and so yeah, we because we took quite a lot of samples from different places, there wasn't that much of a need to account for a change in substratum because of we had a big enough sample size.
Okay. Is there an estimate of how much of the sea floor in terms of area may be impacted by iceberg score?
Yeah, like I said before, we had about 50% that was impacted, and that can vary across the Western Arctic Peninsula as well, and with closeness of glaciers or bays in which icebergs kind of get trapped as well. So the 50% that we have is an estimate from the icebergs impact study that we carry out in Rothera, but there's also another one like that that's being carried out in a different station at an Italian station further up in the peninsula. So it'd be interesting to see what their results are.
Okay, thank you. If anybody's got any more questions for Nadescha, type them in, but for now we'll move on to questions from David's talk. So the first question is, has there been any discussion in using blue carbon habitats in the Antarctic for carbon credit systems or habitat protection?
Carbon credit systems, that's a minefield. So yes, I was talking with WWF yesterday about this very topic, and certainly it is a conversation that a lot of environmental lawyers, particularly in Tasmania, are having, and there was a paper put out about this recently. I think there is a lot of disagreement and a lot of tricky politics to negotiate across nations, and this is often done through CAMLAR, the Conservation Committee for Marine Antarctic Living Resources. So that's a discussion which is being had and hasn't reached conclusion yet. So I think we will get there. I just don't know what form it will take. So sorry for being yeah, we don't have the answers yet.
No problem. Next question is, does iceberg score have an impact on blue carbon that has been sequestered in the seabed?
Yes, it does. I mean, so that's a sort of overlap with ours and Nadescha's work. And there can be positive and negative impacts in that you can put back into circulation carbon which had been put into the seabed, but also with the big mud slumps, you can bury carbon that had been stored. I mean, it's harsh to talk of living animal communities just as conveyors of carbon, but their ecosystem services are a very important functionality in this whole climate solution. And ultimately, their ability to do the job better than we can, even with the most advanced tech, we're inefficient compared with them. And so that may be a very important route to the conservation of biodiversity because of their power as ecosystem services. So, so yes, icebergs can do both. And it depends where they're scouring and how big they're scouring. The scour track itself is destructive, but the margins of the track, the berms of sediment, can be very productive. And the balance is quite different depending on quite what they're impacting. So typical scientist response, it's complicated.
Thank you. Next question, how different is the development of sea ice between Ross Sea and the Weddell Sea?
Oh, I am absolutely the wrong person to answer this. So I will fess up to saying my expertise is really Scotia Sea and Bellingshausen Sea. Anyone that knows either of those seas well knows that I don't know them. So I have worked in the Weddell Sea and I have worked on Ross Sea material. They are similar systems in many respects, in that they are the two places with the widest Antarctic continental shelf. It's about 1,000 kilometers wide in both places. Just think about that for a moment. 1,000 kilometer wide continental shelf. Awesome. And so that means they're very important. It also means they are, because they come very, very far south. It's the two places in Antarctica that you get the furthest south, down to about 74 south. And so it's very, very cold. And so they are both centres of bottom water production. Super cold, super saline water sinks there in both the Weddell and the Ross Sea, flows out because it can't flow south because there's continent there. So it's got to flow north, and it forms the world's bottom water. So if you go to the equator and take a core and put it all the way down to the seabed, that water has come from either the Ross Sea or the Weddell Sea. There's a few exceptions. A little bit has come from Pritz Bay as well. But their overlying sea ice patterns are very extensive, very complicated, and if IPCC can't model them, then I'm damn sure that I'm not qualified to answer that question either. So complicated, and they were both involved in those big reductions in 2014 to 2017, but have both been mildly increasing since. So show me a person that understands it and I'll show you a fibber.
That's a nice segue into the next question, actually. Do you know what happened in 2014 that caused the dramatic reduction in sea ice?
No, I don't. And the most famous paper about this is John Turner and Comiso's 2017 paper in Nature. And their title was Solve Antarctica's Sea Ice Puzzle. And these are two of the leading world experts, and it really is very strange indeed. But sea ice is a complicated thing. There's lots of heat fluxes going on. There are seasonal water levels with different sinking properties and different flow directions. The bottom water is flowing out, intermediate water is flowing in. Intermediate water in the Weddell Sea is different to intermediate water in the Bellingshausen Sea. So they've got different thermal properties, and then you've got a big gyre going on in the Weddell Sea, which in itself is disrupted by polynyas and by different changing sea ice patterns. And then you get breakout of megabergs like A68 that hit the news, which you throw that further into the mix, and they create their own sort of microclimate. It is horrifically complicated. And so, yeah, that'll be 5 in a row where I can't provide a good answer.
Yeah, giving you all the complicated questions, sorry. So we've got a couple more for you. One is, are there any seismic surveys that can be used to quantify the amount of carbon that's been within the sediment column, similar to the work done in Scottish sea locks or shelf environments by Smeaton et al.?
Okay, I don't know that paper, and that sounds very interesting. So definitely worth a look. I think the way we're doing it at the moment is by taking cores and by looking at organic carbon content in one core, inorganic carbon content in another, and then looking at the various contributions to that carbon from different sources like infauna, macrofauna, and phytoplankton and so on. And rumour has it that somebody on this call has a paper in review about that very subject at the moment. But no, that's something for me to go away and look at. And yeah, it sounds interesting.
Okay. And the last question we have here is, are there any comparisons between the Ross Sea and your area with regards to the impact of iceberg scoring? I worked in the Ross on this in 2004, but we looked at depth approximately to 200 to 1,000 meters.
Yeah, so 200 to 1,000 meters is where it's all sort of going on. In that sounds very deep for many of the listeners here. That will sound very deep for a continental shelf. And if it was in this part of the world, that would be continental slope. There, it's shallow. 200 meters is shallow water. The average depth of the continental shelf is about 450. Often the shelf break, the junction between the continental shelf and the continental slope is about 800 meters. So it's very, very deep. So most of the scouring that goes on within that depth band in the Ross Sea is on the shelf break. And much of the Ross Sea's coastal margin is an ice shelf. And all of the ice shelves in the West Antarctic Peninsula, our region, have gone. There's only tiny fragments left. So there is a lot of inshore scouring in the West Antarctic Peninsula compared with the Ross Sea. It's much, much more dense scouring in the shallows, but the scouring on the shelf break is less than the Ross Sea. So the Ross Sea gets quite a lot of bergs that are homegrown from breakouts from ice shelves, but it also gets a fair amount from the Weddell Sea, which, if you look at a map, is kind of surprising given that it's thousands of miles away. But the Antarctic circumpolar current and the jets that comprise that, which is the biggest current system in the world, carry the bergs round. So if a megaberg breaks out in the Weddell Sea and doesn't ground out on the Weddell Sea shelf, it tends to be carried in a current round to the outer margins of the Ross Sea. So the shelf break there does get fairly peppered. And the shelf break, I mean, if I showed you a picture of the shelf break on the West Antarctic Peninsula, you'd be pretty impressed. It's absolutely crisscrossed, which, considering it's 400 meters down, imagine the size of the iceberg that's required to scour at 400 meters. And you might think they're vanishingly rare, but the last time we were there was one doing exactly that. There was a grounded iceberg in 450 meters of water. I mean, pretty impressive, and a little bit scary, to be honest, because these things are quite dynamic and can break up. So the trick is that in comparing those two regions, you're trying to compare modern scour with not so modern. And when I say not so modern, since the last glacial maximum and the retreat of ice, then any scour done anywhere is going to be preserved. So there's 25,000 years worth of scours on the shelf breaks, and we have to interpret what's going on now compared to what's happened at any point previously in that 25,000 years, which is very different from very difficult using multibeam, the picture that Nadescha put up. So we can use radar to look at the topography of these scales, and we can see which cross which to look at the most modern ones. But the most modern ones could be 2,000 years old, or they could have happened yesterday. And really, we need cameras and we need direct sampling to do that. But direct sampling is very expensive in time and space, and you can only do so much of that when a research ship costs about 25 grand a day. So no, there hasn't been a lot of comparison of the scour intensities of those two regions, other than the broad brush that I'm painting.
Thank you. There was a slight amendment to that question as well. So this person worked between 50 and 750 meters, and we found most scouring happened between 250 and 750 meters, roughly 60% compared to approximately 1%. And we found approximately 1% we found in shallower water. But thank you very much for.
Wow, that's incredible. So that really is hugely different. And it would be really nice to see that paper. So if they could pass the paper to Nadescha and forward it on to me, or, to be honest, if you Google me, I'm sure my email address will appear very easily.
But thank you very much both for coming in. A really interesting talk. Thank you very much.
Okay, thank you.
Cheers all, and thank you for listening.